This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Draw a line between incompressibility effects and compressible effects. So in that case, there's no shock wave because you could keep the aeroplane stationary and move the fluid, and it's moving with respect to the fluid with a velocity, but that velocity is less than the speed of sound. So it's not supersonic flow, and so there's no shock wave. In that case, we can say that the total pressure that the pitot tube would measure would be PT1. It would be the same as the total pressure without a shock wave, and that'll be the stagnation pressure, P0. And the ratio between the total pressure and the static pressure for an isentropic flow, you've seen me do it before, it's 1 plus gamma minus 1 over 2 m squared. All right, so now that would enable you to measure, if you could measure the total pressure with a pitot tube, you measure the pressure, and if you could measure the static pressure, and I'm going to tell you how to measure the static pressure in a minute, then that would lead you to the Mach number squared from this relationship here. But the question then would be, how do I get the velocity of the aeroplane? And I might actually want to know the velocity of the aeroplane. So here's how you do that. You measure not only the total pressure and the static pressure, you also have to measure the total temperature. And I think I said that just at the end of yesterday. We know that for isentropic flow, the ratio of the total temperature, which is the enthalpy based on the enthalpy when you bring the fluid to rest, divided by the static enthalpy, and you know that HT is H plus a half U squared. So that's where the gamma minus 1 comes from. So given the total temperature, so if you could measure the total temperature, and from the static pressure and the total pressure you know the Mach number, then you can see from this equation here, since I know the total temperature, since I know the no, it's not working. I'm sorry. It's irritating. It doesn't work. Since I know the total temperature and the static temperature I don't know, but I do know that the ratio of the total temperature to the static temperature is the speed of sound. You know that the speed of sound is the square root of gamma RT. So the total temperature is gamma R is AT squared, and the R's and the top and the bottom cancel, so that the ratio of the speed of sound, total speed of sound squared to the speed of sound squared will be 1 plus gamma minus 1 over 2 m squared. Yes?
How they measure the total temperature? Is it normal thermocouple?
Frequently it's a thermocouple, yes.
When they bring the fluid back.
So they've got to bring the flow to rest. Ideally, it's very difficult to measure the total temperature, as I said to you, because you have very large gradients in temperature in that region, and they give heat fluxes. And so assuming isentropic flow may be a poor approximation. However, that is what is done. So you try to measure the total temperature, and that depends on the Mach number squared. So I can therefore solve this equation for the static temperature.
Hey Gary, you actually changed the mode. Don't hold down the bottom button. Just press that top one there.
Oh,
yeah.
Thank you.
Yeah.
Oh, you've got it there. Thank you. So if I know Mach number squared from the pressure, I therefore get the temperature, or I get the speed of sound squared. And so if I'm given the total temperature and the Mach number, that leads to, in this equation, leads to a squared. And if I know a and I know the Mach number, then I get the velocity. So that's how you get the velocity of an aeroplane flying subsonically. What if the aeroplane was a fighter aeroplane and flying supersonically? How would you do it? So now there's a more serious problem. So let's think a little bit about all of this. The total temperature divided by the reservoir pressure P naught, that will be, the reservoir pressure, that will be the total temperature in region 2 divided by the total pressure in region 1, because PT1 is the same as the stagnation pressure. And I've just proven to you from the entropy relationship, I showed you that this ratio of total pressures was also given by the ratio of the static pressures and the ratio of the densities, all to the gamma, 1 over gamma minus 1. So I have found for you the relationship between P2 and P1 for the shock wave, and it was P2 over P1 was 1 plus 2 gamma over gamma plus 1 m1 squared minus 1, so P1 over P2 is 1 upon that. And I also found for you the relationship between rho 2 and rho 1, and that was in terms of m1 squared, and that's to this power gamma here, and then it's all to the 1 over gamma minus 1. So how does this work for a fighter aircraft? So if you were in a wind tunnel and you knew the upstream reservoir pressure, then that would be PT1. And if I measure PT prime, which is PT2 in region 2, then I have an expression here. I could find Mach number 1. So I could find, if I were in a wind tunnel, I could, and I knew the upstream reservoir pressure, and if I knew PT1, then I could find M1 by measuring PT prime. So I could get the Mach number, and I also have to measure the total temperature by the same trick as I did before in the subsonic case, and I can get the speed of sound, and therefore, since I know the Mach number, I know the velocity. However, if I'm in a fighter aeroplane and I'm actually flying, I have no upstream reservoir. And so I'm in free flight, or I might have non-isentropic flow from the reservoir, even in the wind tunnel. And I also need then to measure the static pressure. So now, if I could disturb the flow without a shock wave, then the relationship between the total pressure for isentropic flow and the static pressure is 1 plus gamma minus 1 over 2 m1 squared, and the temperature, the ratio of the temperatures is 1 plus gamma minus 1 over 2 m1 squared, and the pressure goes like gamma over gamma minus 1. So I could get, I have this relationship between PT1 and P if I had no shocks, So I have to devise a technique for measuring the static pressure in supersonic flow without shocks. So that's subtle. I'm going to show you how it's done. So if I combine this equation with the equation I had before, so I had PT2 over PT1. I don't have P naught. So if I multiply that by PT1 over P, and I measure P, then I can get the Mach number. So that's how it's done. So I multiply that previous result by this equation 2, and I get an expression for PT prime over P. So what I need to do for this supersonic fighter aircraft is measure the total pressure with one probe, and I measure the static pressure with another probe, and I then have to measure the total temperature, and from the total temperature I then get the speed of sound A, given the Mach number, if I know the Mach number. So I get the Mach number from this, the total pressure and the static pressure. I get the Mach number from that. I get, and I put that Mach number into the relationship between the speed of sound, AT squared over A squared, and that gives me A, the speed of sound, and then if I multiply A by the Mach number, I get the velocity of the fighter aircraft, and I might need to know it. So now that equation that I've written down there for you is equation 6.3 in Liepmann and Roshko, and remarkably Lord Rayleigh worked it out. It's incredible, really. This is not new stuff. This has all been known for quite a long time. Lord Rayleigh, and this is his, quote, supersonic formula. And so how do we measure the static pressure? So this is important. In subsonic flow, so the flow, we don't have any shock waves, then we just have typically a pitot tube is a combination, or pitot-static tube, in fact, is a combination of a pitot tube which measures the stagnation pressure right here, and way down here you have some holes that go to a duct on the outside, and you typically have holes all the way around, and that is isolated from the tube inside, which is measuring the total pressure, and the static pressure is being measured here because you don't have any shock waves and the flow is essentially horizontal and is undisturbed, or that's the assumption that it's undisturbed. So you're measuring the static pressure. So that's what you do for Mach number less than 1. What do you do in supersonic flow? You know that you're going to have shocks in a supersonic flow. We've got to bring the fluid, if we're going to change it at all, we're going to go through a shock. Now, I haven't yet done, but you're going to see me do next week an oblique wave, where we have an oblique wave. And if you turn the flow by a very small angle, then the shock is very weak. And if the shock is very weak, we know from what we've studied already about shock waves that they're essentially isentropic. So if we turn the flow just a very small amount, and what we're going to do, we're going to turn it, if we have an object that looks like this in supersonic flow, we're going to turn the flow here through a shock wave, and then we're going to expand the flow out here through an expansion wave, and you can guess that a very weak compression and a very weak expansion are all isentropic. And so this will be an isentropic relationship here. There'll be no shock waves, and I'll measure the static pressure here where the flow is parallel, the same as it was up here. And so I'll measure the static pressure there. And typically that is about 10 to 15 diameters. So that's how it's done. All right, now the next application of shock waves that is also terribly important and could easily be in the context of steam, and we don't have a perfect gas, or it can be in the context of a solid rocket motor, and the solid rocket motor has combustion gases which are anything but air. So how does that work? Well, you'll remember that we talked about this Laval nozzle, and it's discussed in Liebman and Roshko in figure 5.3, if you want to see another conversation about it. I drew this picture before. If I plot P over P naught, if the flow is everywhere subsonic, then you get an acceleration here to the highest velocity at the minimum area, and then the velocity decreases in subsonic flow. And you come back here, and this difference between the stagnation pressure here is the dynamic pressure, a half rho u squared, and if I divide it by P naught, this will be the gap from 1. So that's the incompressible flow result here. And the limit of that is when you keep dropping this downstream pressure here, PE, and you drop it further, and the flow keeps accelerating because you're dropping the pressure, and there's a greater pressure gradient, so the flow keeps accelerating, certainly up to here, and then it decelerates here if it's subsonic here. So if we keep it just less than sonic here, we have this curve, or we finally come down to reach this point here where we reach Mach number 1 here, just less than Mach number 1, and now it recovers as a subsonic flow here, and the pressure recovers, and we finish up here at C. On the other hand, if I drop the pressure PE very substantially below this point here, then I have Mach number 1 here, and all that I've done gives me supersonic flow in here, and that takes me on this branch here. So now, I posed for you last time, what happens if the pressure is exactly PJ, less than PJ, or as high as the pressure at C. So this is very basic to rocket nozzles. So if the exit pressure, PE, is exactly equal to PJ, then you say that this supersonic flow is correctly expanded. Now, if you have a rocket nozzle and you're at various places in the atmosphere, if J were much less, so you're in the upper atmosphere, if the exit pressure is much less than PJ, so if PE is equal to PJ, it's correctly expanded. If PE is much less than PJ, then this jet is underexpanded. It means that I could have had further area in which I expanded the gas even further and got to higher velocities, but I didn't, for reasons that you can think about in this rocket nozzle. PE is less than PJ, so it's down here somewhere. Then what happens is that the flow, the pressure's too high and it wants to turn out, and we will find that if you turn the flow, the pressure falls. So it will turn through an expansion fan, and the pressure will drop, and you'll get a whole expansion fan there, and then you'll have to turn the flow back because the main flow is still supersonic, and you'll have shock waves. So if PE is less than this pressure here, PF, but greater than PJ, the pressure adjustment is through oblique shocks downstream. Oblique shocks. You have to turn the flow and you have oblique shocks. And if PE is exactly equal to PF, well, you now know what would happen. If PE was exactly equal to PF, then that, and the pressure jumped from there to there, then that would be through a normal shock. So there is a normal shock at this Mach number would produce this pressure here, and so a consistent picture would be an exit pressure at PE equal to PF. You'd have a normal shock here.
Gary, but based on the pressure differential, a shock can form in the actual diverging part of the nozzle, right?
Yes.
So what determines whether or not it will form at some part of the nozzle,
right,
or whether it will just continue to expand and then at the exit?
Yes. Well, once you get something there, you can propagate the pressure field upstream. And you certainly can have, this is not guaranteed that you will have what I've described, just a normal shock. It's frequently more complicated than that because there are boundary layers, and the boundary layers, the pressure rise will cause the boundary layer to separate, and you get oblique shocks, and so there could be a mess inside there. And the assumption, people don't want to have normal shocks in this nozzle, even though they are bound to when they launch the vehicle, because it can lead to instability. It can drive the pressure from the axis, which is what you'd like to have in a rocket, and if it's off the axis, then you have to try and bring it back by gimbaling the rocket nozzle. And you can run out of, as I mentioned on the Titan IV, that's exactly what happened. They ran out of gimbal control. Yes?
When we have the case where PE is between PF and PJ,
Yes?
can we say that it always happens at the exit, or it can be inside of it?
It'll probably be downstream. I don't think it can be certain because the boundary layers can play a role. And so you're going to feed, because they're subsonic right at the wall, you'll feed that downstream pressure upstream. So, but typically, yes, it'll happen downstream. You'll get the adjustment downstream.
Okay, sorry, is the PE the exit pressure?
Yes, it is.
Prior to or after the shock?
That's after the shock.
After the shock.
Yes.
And do the FJ letters, do they reference the curve or the pressure?
It's the, at J, it's the exit pressure in the supersonic flow, which is exactly matched to the exit pressure, right? So you have a supersonic flow and zero velocity on this side. It is a classic example of a turbulent shear layer that develops. You'll have much higher velocity here, zero velocity here, so you'll have a shear layer in between. But it's potentially a solution that you have parallel flow still in the free stream. You have a shear layer, and then you entrain into the shear layer below it. So that's the reality of what would really happen. So it could be, you may get a weak wave there. But this is the ideal case, non-turbulent.
So PE here is the same as the ambient pressure?
Yes, PE is the ambient pressure. So when the pressure in the supersonic nozzle at the exit J is exactly equal to the exit pressure, you can imagine that you could have in inviscid fluid a slip line. No normal components of velocity, and therefore no gradients in pressure. And I don't need any shock waves or anything there. So that's this idealized case where I have a slip line between the fluid that's coming out, and it'll have the same static pressure as at the exit, unless, the flow's not parallel at the exit. But if it's parallel at the exit, then you'll have this J, Pj. And you'll have parallel flow, slip line, and the same pressure outside, static pressure. So that would be the case of a correctly expanded supersonic nozzle. If PE is even less than PJ, then we've underexpanded, namely we could keep expanding some more until we reach PE. If PE is greater than PJ, it's overexpanded. We kept expanding it as a supersonic flow for too long. We should have cut the nozzle off if we didn't want shock waves. And if PE is between PJ and PF, we know that a solution to our equations anyway is a normal shock at the exit. That would be conceivable. If we have a normal shock at the exit, then we will jump the pressure up and it'll go up to PF, right? And now what happens if the exit pressure is higher than PF but still less than PC? The exit pressure is higher than PF but less than PC. PC, you remember, is right on the cusp of the case where the whole flow is subsonic. So this case that is soluble in terms of our equations, we could manage it by having a normal shock in the throat at some point, and then because we know that the flow behind that normal shock is subsonic, then this expanding area will mean the flow will slow down and the pressure will rise. The pressure rises as the flow slows down in subsonic flow. And so I've drawn these lines here. So this is the pressure rising in this continuing expanding area because the flow is subsonic. And I can have E and D in here until I reach this entirely this is the boundary between M equal 1 at the throat and M equal 1. The only place M can be equal to 1 is at the throat, the minimum area. Right, so that's the picture that emerges. And now I want to turn the problem around because you've heard me say that we're going to define dP rho as A naught squared. And some of you may have asked, well, why the hell did he do that? What on earth is the relationship between dP rho and A naught squared and the actual speed of sound? So I thought I should say something about the actual speed of sound. So now we're going to talk initially about an unsteady problem, but it has a shock wave in it. And the shock wave, instead of having the shock wave stationary and the flow moving into the shock and then being downstream of the shock, I'm going to turn the problem around so that I had the flow where the flow was supersonic coming into the shock. I had the shock, and then I had a subsonic flow. That's what I looked at. I had a steady state case. What if the shock wave were moving? How could I set that up? So let's talk about the very, very fundamental ideas of an XT diagram and shock tubes and shock waves. Shock tubes have been used in the study of all kinds of compressibility effects. So how does it work? So let's turn the problem around. So what I'm going to suppose for you is, let's suppose, so what I've said here, I may get a chance to show you why a shock wave forms. It's a little bit subtle. In the case of gas dynamics, I would need the method of characteristics, and I don't think I'm going to get very far with that for you. I may be able to do it in the context of acoustics, which is where it all began. So here now is the idea. I've got some tube here. So here's my tube, and I've got downstream here a fluid at rest. Here's, I've just arbitrarily made a downstream boundary at x1 of my control volume, and here's my upstream boundary at x2 of the control volume. But I'm going to imagine that I could set up a case somehow where I could drive a shock wave with a speed us into this flow that's not moving. So the shock wave is going to move with a speed us. And what I'm going to expect to happen is that the density after I've come through the shock would be a little higher. The pressure would be higher than the pressure downstream here, because the flow has come through the shock wave, and I'm expecting the pressure to be higher. So here I'm going to suppose that I have a velocity of the gas u2. I've got a density ρ2 and a pressure p2. And here I've got a density ρ1 and a pressure p1, but the fluid's not moving, but the shock wave is moving. All right? So how would you relate that to a stationary shock? Well, if I subtracted, if this is a steady state case, then I can make a Galilean transformation and none of the forces change because there's no accelerations in the problem. So if I subtracted us, the shock would be stationary. This fluid now would be moving to the left. This fluid would be moving to the left. So we're going to see that that's the same thing. But I want to set it up as an unsteady problem. And I want you to be able to follow in detail how I use my conservation laws to solve the problem. This is a good example of how well you understand them. Right. So what is the conservation of mass in words? The rate of change of mass in the volume plus the net flux out equals 0, right? That you have to know in words. So now we're going to work it out. So what is the rate of change of mass in the volume? I've got to calculate the mass. How do I calculate the mass? If I integrate, if this was unit area, then the volume, I'd find the mass by integrating the density from x2 down here all the way up to x1. So that would be the mass, rho per unit volume, and then I'm just summing up all these little volumes, dx. And I want the rate of change of that, and I have the flux of mass across this surface out, and since u1 is equal to 0, the flux would be ρ1 u1, but u1 is equal to 0, so that's 0. The flux of mass across this boundary out is plus or minus. And why? Why? Because the normal is out and the velocity is in, so u dot n is minus 1. So that's minus ρ2 u2 is the flux of mass across this boundary, and that must be equal to 0. So now we're going to work out, and this is easy to do, this integral from x2 to x1. Well, the only thing that's changed here is that this shock wave moved from here to here. So I've suddenly got more fluid here that is at density rho 2, and I've got less fluid that was at density rho 1. So I can do that easily. The volume that's now at density rho 2 is US delta T rho 2. And I've got less at mass rho 1, and that's the volume US delta T rho 1. So now I've got to take ddt of that. Well, if I divide by delta T and take the limit as delta T goes to 0, then the delta T's are going to cancel here. So I can do that. And I get, therefore, rho 1 US, so if I take this to the right-hand side, rho 1 US is equal to rho 2 US minus U2. So that's it. Well, that's also what you could have written down immediately by taking a Galilean transformation, and you said, all right, here's the case that I was looking at. I can make it a steady flow if I subtract US. So this becomes V2 is U2 minus US, and this becomes V1, which is U1 minus US. So V1 would be the velocity in here. So, and you can see that V1 is minus US, and V2 is U2 minus US, and so this is the same thing as minus rho 1 V1 is equal to minus rho 2 V2, which is what we wrote down for our steady case. So we recover rho 1 V1 is equal to rho 2 V2, where in the steady case I've called these V's in this direction. So all of the results that I've worked out for you for a stationary shock can be applied here. You just have to be a little bit careful. So I wrote down for you that P2 minus P1 was rho V1 squared minus rho 2 V2 squared, and H1 plus a half in the steady shock case. These V's are distinguished from these U's. But let's work it out, make sure that even those cases, the Galilean transformation works. Let's be absolutely sure. So, what's, in words, the control volume statement for the momentum equation? I don't hear anything. Come on. You can say anything you like. If you say I haven't a clue, then that's okay. I was at pains early in this course to really emphasize this. The rate of change of momentum in the volume plus the net flux of the ith component of momentum is the net force on the volume. Very, very important. You'll never get a job as a consultant in industry unless you can say those things standing on your hands. So let's apply it. The rate of change of momentum in the volume, well, the rho 1 U1, and this is just the same thing as I did before. You've now got rho 2 U2 and it's moving with US. And the shock wave moved at US delta T, and so the volume is, and so the rate of change will be US delta T divided by delta T, and so I'll just have US. And the net flux out, there's no flux of rho 1 U1, and there's only a flux of minus rho 2 U2 squared, because it's the flux of mass is minus rho 2 u2, and the velocity is in the positive x direction. So we can write that down. P2 minus P1 is the net force in the x direction. P2 minus P1 is rho 2 u2 us minus u2. Well, now that's interesting because I can go back up here and I wrote that rho 1 us from conservation of mass was rho 2 us minus u2. So I can rewrite that rho 2 us minus u2 is rho 1 us multiplied by u2. So that's very interesting. If I have a very weak wave, then the delta P, the change in pressure across the shock, would be very small. And it's equal to rho 1, which is not necessarily small, us, which is the speed of sound, roughly speaking, which is not small, but it's times delta U. So delta U is very small if delta P is very small. So there's very little. If I have a weak shock, the velocity behind the shock is very tiny. So that's an important idea, and we're going to work that out. If we do the energy equation, and I've done it here for you, what is the energy equation in words? The rate of change of energy in the volume, but now the energy is the internal energy plus a half u squared. And this rate of change is going to give me a us delta t, and divide by delta t to take the derivative with respect to time. I'm going to get this first term here. And the net flux of energy out is the only case will be minus rho 2 u2. Minus rho 2 u2 because it's negative mass flux and it's carrying h2 plus a half u2 squared. So now this is a little tricky because I've got the internal energy here, rho 2 e2 and rho 1 e1. Well, you remember the definition of the enthalpy. The enthalpy is H is E plus P over rho by definition. So if I multiply this by rho, I have rho H is equal to rho E plus P. So rho E is rho H minus P. So I could write this rho 2 E2 is rho 2 H2 minus P2. And similarly, this rho 1 E1 will be minus rho 1 H1 plus P1. But I've worked out what P2 minus P1 is up here, so I can put that in, and it's rho 2 U2 US minus U2, rho 2 US minus U2, and there'll be a half U squared. Oh, I think that's coming from it's coming from here. Okay, anyway, you can do that and you get the energy equation can be written in that form, and if you divide throughout, if you write it in this form, if you divide throughout by rho 2 US minus U2, I can divide it out and I get H2 minus H1 plus a half U2 squared minus U2 US equals 0, or H2 minus U1 is US minus a half U2 multiplied by U2. And that's the same thing as the result that I had before. H2 minus H1 is a half V1 squared minus a half V2 squared. So it's the same as the previous result. So all of the previous results go forward, not surprisingly. All right. Now let's just do a couple of things here. I just want to explain to you that delta P, from the previous work that I've done, the change in pressure is 2 gamma over gamma plus 1, m1 squared minus 1. And for delta P, if you have a very small change in the pressure, it's a very weak wave, m1 squared minus 1 is epsilon. I showed you that last time. M1 squared is epsilon, or M1 squared is equal to 1 plus epsilon, and epsilon's going to 0. So delta P over P is 2 gamma over gamma plus 1, and M1 squared minus 1 is epsilon. So the pressure rise is very small, and I can change this delta P, and I can change the P to gamma, gamma dividing by P. Gamma P over rho is the speed of sound squared, so the speed of sound is gamma 1 over gamma times the P. So that's why I put it down in here, and I can play around here, and I get this relationship. Anyway, the point that I want to make simply is that the velocity behind this shock wave is terribly small. U2 gets very small, and U2 divided by A2 is of the order of 2 epsilon over gamma plus 1. So if epsilon is a very small quantity, the pressure is a very small, pressure change is very small because the pressure change is proportional to epsilon. If that's very small, pressure change is very small, then the velocity divided by its speed of sound is very small. So I get to this point that I want to make. Thus, a weak shock would be the limit of a small piston motion. So here's the idea. So this is the XT diagram that I wanted to get to today. So here's my piston. So here is X, and here's time. And the piston starts here at X equal to 0. And t equals 0, so it starts right here. And then it starts to move with a velocity u2, a very tiny velocity. So that causes a pressure rise in all of this fluid here, and a weak wave to propagate into this fluid at rest. So here's the weak wave. This pressure, if this pressure downstream of this weak wave is P1 and the velocity is 0, then I've got a weak wave, and right behind it the pressure is P1 plus delta P, but that's a very small quantity. And U2 is the velocity of the piston, very small quantity. So that's the basic idea of a shock tube, but it's a shock tube, a linearized shock tube for a very, very small piston motion. I could make this piston move terribly fast. How could I do that? Supposing, here's how a real shock tube works. Supposing I had a high pressure tube and a low pressure tube, and I separate them by a diaphragm, which is a very thin, say, aluminum sheet that separates the high pressure. And now, downstream in this low pressure region, I have high altitude, low pressure, and I have a mixture of air and something else because I'm interested in shock waves in air. And now what I do is I start to pressurize the high pressure region where my diaphragm is. So I keep pressurizing it and I keep pressurizing it, and I'm quite clever. I know that my diaphragm will distort, and I have waiting for it to distort a cutter, which is a very sharply edged, highly sharp steel cutter. So the diaphragm begins to distort, and suddenly it rests against this crucifix, which is a cutter, and of course it can't take the pressure and it ruptures. So this diaphragm ruptures and I get four petals forming from a typical diaphragm crucifix. And those go back against the wall, and now I've got all of that high pressure behind moving something downstream. And it drives a very high intensity shock wave. Can do. So this is, we could understand all of that by drawing an XT diagram, and I'm not going to have time to do that. So, for a very weak wave, you've seen that this pressure rise is ρ1 US times UP, and we've shown that the velocity of the shock approaches the upstream speed of sound, A1. US approaches A1. So for a very weak wave, delta P is ρ1 A1 times the velocity UP of the piston, but this is very small, so UP is very small. And, well, I'm not going to say too much about it, but US over A1 squared was V1 squared over A1 squared, which was M1 squared, which was 1 plus gamma plus 1 over 2 gamma delta P over P1. And this was going to be equal to 1 plus M1 squared was going to be equal to 1 plus epsilon. So this says that US over A1, and I'm just going to take the square root of this, and if this is a very small quantity, then this is gamma plus 1 over 4 gamma delta P over P1 for this very small. And since S is a constant for a very weak wave, P goes like rho to the gamma, and so delta P delta P over P goes like gamma delta rho over rho. Just take the logarithm of that and then differentiate it. You'll get delta P over P goes like gamma delta rho over rho. And so delta rho over rho is 1 upon gamma delta P over P, and that's going to be U2 over A1. Well, you can just evaluate that. And delta T goes like gamma minus 1 over gamma delta P for isentropic flow. And you can also take the very strong shock limit, which we've worked out before, where M1 squared will be gamma plus 1 over 2 gamma, P2 over P1, so this is P2 is much greater than P1. So it's a very strong shock limit, and therefore US is equal to A1 into this quantity here, gamma plus 1 over 2 gamma, P2 over P1 to the half. And I can also use my relationships for T2 over T1 and the relationship I had for strong shocks of ρ1 over ρ2. And that was gamma minus 1 over gamma plus 1 is the ρ1 over ρ2, and this P2 over P1 I've just written down for you here. P2 over P1 is this one here. So that I'm going to quit there. You can also find, for a very strong shock, how large is U2 over A2? And I said for a very weak shock, it's arbitrarily small, but what about a very strong shock? Well, U2 over A2 will be V2 over A2 because U2 is V2 plus US. It's V2 over A2 plus US over A2. And so that's US over A1 by A1 over A2. So I can fiddle around here. I get this final result, answer that U2 over A2, the maximum I can get for a very strong shock, is, if I evaluate all of this, it's 2 over gamma into gamma minus 1 to the 1/2. So for gamma equal to 1.4, this is 0.4, and you can show that, or gamma is equal to 7 over 5. This when I take the square root, I get 5, the square root of 7 over 7, and it's 1.89. So the maximum Mach number you can get behind this very strong shock is 1.89. So for a strong shock propagating into a perfect gas at rest, the maximum Mach